All right, in this video, we are going to start Notes 8 of Calc AB. It's about L'Hopital's rule, which is another method of evaluating limits, in particular limits where you get 0 over 0 indeterminate forms, or infinity over infinity, or maybe negative infinity over infinity, or infinity over negative infinity, whatever, like the absolute value of infinity over the absolute value of infinity type thing. So we're going to start off with some limits that like maybe do, maybe don't require it. Let's see if we can evaluate these. And we'll kind of go from there. So we want to evaluate them. So I can think of two ways to evaluate this limit. I can think of a lot of ways to evaluate most of these limits, actually. But we only need one. But I'm going to do maybe more than one. So maybe you look at this and you think, I know how to factor that, right? So first of all, check, right? You're always checking before you're doing. So 0 over 0. Okay. Yes, we get 0 over 0. We're allowed to do stuff. Otherwise, it could be a trick question where like you plug it in, you just get like 5, and that's your answer. So I'm going to say that this limit is the same as, so it's x minus 3 and then x squared plus 3x plus 9 all over x minus 3. So I remembered how to factor that. If you don't remember how to factor it, I think the most reliable way to do that is by doing synthetic division, probably. So this is actually the same as x squared plus 3x plus 9, which would give me 27. Okay, so let's say I didn't remember how to factor it. If I didn't remember how to factor it, I would have done this. I would have said, whoops. So like since I got 0 when I plugged 3 into the numerator and the denominator, I know that x minus 3 is a factor of the numerator. So like I'm confident that I can factor it somehow. So I'm going to do this. And then 1, 0 for squared, 0 for first degree, minus 27 here. So bring this down, 3, bring it down, 9, bring it down, 27, bring it down, you get 0. So that gives me 1x squared, 3x's, and a 9. So you could use synthetic if you need to. Another way that I can think to do this particular problem is I look at that and I think that has a very specific form. I actually think this is the limit definition of the derivative. I think that we can look at this limit and say that if f of x is x cubed, this is just asking for f prime of 3. And it definitely is. So f prime of x would be 3x squared by the power rule. So f prime of 3 would be 27. Either way, we're getting 27. So these are valid ways of evaluating limits. It's actually really common in AP calculus in particular to evaluate a limit by recognizing it as the definition of the derivative. So here, let's see. So what are we doing? Well, it's the limit as h approaches 0. So immediately I'm thinking this is the definition of the derivative. If it is the definition of the derivative, what's my function? Well, it would be f of x plus h minus f of x over h. So I think that my function must be this. So I'm going to say that f of x is cosecant of 3x. And I'm looking for just the derivative of cosecant. So I want f prime of x. And the derivative of cosecant is negative cosecant cotan. But then chain rule gives me a 3. And I'm just going to leave that like that. I mean, I could rewrite it as negative 3 cosecant cotan. It looks better, so I'm going to do it actually. It's all about looks. Not really. It's about like ease of use, I guess. And I think it's easier if the 3's in the front. All right, so all this was asking for was the derivative, right? This, you want to get amazing at recognizing the limit definition of the derivative. It's one of the rare things where you can almost abbreviate every word, but limit definition of the derivative, definitely. That's a very common way of evaluating limits. All right, let's see. So here, limit as x approaches negative infinity, square root of x squared plus 5 over x plus 3. This is maybe my least favorite type of limit to do because it's kind of like impervious to all of the techniques that I want to use. Like, am I going to rationalize this? Probably not. So what I'm going to do, I actually don't know if rationalizing would work on this. I don't know what that would even really mean. I like to use the following technique. So this is a technique that I use all the time on a radical type thing, going to positive or negative infinity. What I do is I try to take out of the radical the highest power of x that makes sense. So I'm going to say that this radical I could think of as x squared and then 1 plus 5 over x squared and then over x plus 3, right? All I did was factor x squared out of everything in the radical. So now what I'm going to do is the limit as x approaches negative infinity. The square root of x squared is the absolute value of x. So I take that out, and then I still have 1 plus 5 over x squared over x plus 3. All right, now, big step. If x is going to negative infinity, what's the absolute value of x, right? Absolute value of x is x when x is greater than or equal to 0. It's the opposite of x when x is less than 0. So because of that, we can make this leap and say, if x is going to negative infinity, x is definitely negative, which means we can replace the absolute value of x. We can replace this with this because we're going to negative infinity. If we're going to positive infinity, we'd replace it with x. So that's a big step on this. So x is going to negative infinity of negative x radical 1 plus 5 over x squared all over x plus 3. Now what do? Well, now I'm going to divide through by the highest power of x in the denominator, always the denominator. So divide everything you see by the highest power of x in the denominator will give me still limit as x approaches negative infinity. So in the numerator, I can either divide negative x by x or I can divide the radical, but I cannot divide both. So I'm going to choose, obviously, to divide negative x. So it gives me negative 1, but I'm not going to write that. And then 1 plus 5 over x squared over x is 1, 3 over x is this. Now, if you go to negative infinity, 5 over x squared goes to 0, 3 over x goes to 0, so we're just left with negative 1. So that's our limit. You know what's terrible about that limit? It never really gets better. You don't learn like some super secret technique that you'll use later on. Like, it doesn't happen. It's just like that's what you got to do. Okay, so how about this? So I can kind of think of two ways to do this, kind of, but one of them is I just have it memorized, right? I have that memorized. Limit as x approaches 0 if sine of x over x is equal to 1. That's like a famous limit, and you should probably know it. I do see, I think, another way that I don't usually use on this, but what if we rewrote this? So, or new color, right? So this is memorize. So the next thing I'm going to do is like exceedingly weirdly clever, perhaps, or maybe it won't work. We'll find out. I'm going to rewrite it as the limit as x approaches 0 of the sine of x minus the sine of 0 is actually 0, so like minus the sine of 0, sure, over x minus 0. What? This is f prime of 0, but for what function? For f of x equals sine of x. This is the other definition of the derivative, right? So the derivative of sine is cosine. So your ability to do this is contingent upon your knowledge that the derivative of sine is cosine. But if you do know, so then f prime of 0 is the cosine of 0. The cosine of 0 is 1. That's another way you can do it, but you got to know that derivative to be able to do it. So either memorize it or that I just have it memorized. I think that's the most useful way to do it. But this is a really interesting way to look at it, as like, always look for the like minus zeros, like, because sometimes when they're not there, they're really there, and then you can like do some stuff with it. So that's what I did here. All right, so each of these was like slightly different. So for part A, I had to do something. I had to factor or synthetic division. For B, definition of the derivative, that was like pretty clear, I think. C is just like never going to get better, and that's too bad. For part D, you either know it or you don't, or you're super clever, right? Or maybe you're like a geometric master and you can come up with the geometric proof for that limit, which like I can never really remember offhand, but I do know that the limit is 1. Now, what I didn't do, and I should have done all the way through because I'm about to be asked that question, is I did not in every instance check to see if originally I got 0 over 0. Here I don't get 0 over 0. I actually get, what do I get? Infinity over negative infinity, which is kind of weird. And here I get 0 over 0. So now I did. So now let's see what the next question is asking, because I didn't want to have to answer that in the negative. So the thing that's true about all of them is they are all indeterminate forms. They're all 0 over 0 or infinity over infinity. And because they were like that, we were allowed to do other stuff. If you try direct substitution, you get an answer and you're done. If you try direct substitution, you get 0 over 0 or infinity over infinity. It's like you need to do more work. So I'm going to come back in the next video and explain a little bit about a technique that we can definitely use to do that work in these particular cases. So it works for 0 over 0, infinity over infinity. I'll be back and we will talk about it. So I'll see you then.